Hello again. We'll continue here our discussion of the Connecting Rod project to discuss the following steps on the last lecture. So let's see here. As we mentioned before, our idea is to review the Connecting Rod project and then to talk about grading and reporting. So the steps that are needed in the project, we discussed load analysis, and we will finalize our discussion of what is entailed in the application of beam theory, where we're going to discuss dynamics, and then we'll talk about the next step beyond hand calculations, and that is using the finite element program, COMSOL. And then we will discuss how we would optimize the connecting rod, the geometry and the dimensions, using a variety of techniques involving life assessment with fatigue and fracture. And the optimization is going to lead to a final product that we can build in a 3D model. So we'll have a CAD model 3D, and that finally would be analyzed with Abaqus as an additional program to give us some kind of additional experience. So let's see here. Talking about the dynamics, we need to determine the forces that are acting on the connecting rod and also the moments or the torques that need to be included in load analysis. So dynamically, the connecting rod is going to be included as mass, concentrated mass at the center of gravity. And the CG is going to be obtained from the detailed configuration of the connecting rod in 3D, and that we could easily obtain from software, SOLIDWORKS, for example. So once I have the mass and the center of mass of the connecting rod, we're going to assume that the mass is concentrated at that point, and this point is G, and we would consider it as a particle from a dynamical standpoint. And then we have another regularization for the piston, where we will simplify the piston as another particle that has a position P, and therefore the piston is going to be having a mass. So we have the mass of the piston here, and it is moving with an acceleration that is described by this position, the second derivative of the position with respect to time. That is the acceleration. Similarly, the connecting rod has a mass mg, m of the connecting rod, and it's moving on the acceleration. So these are the two reduced particles that we need to describe for the motion that determines all of the forces on the rod. The forces on the rod, we have reactions from the piston on the rod, and we have reactions from the crankshaft on the rod. So the crankshaft is going to be assumed to have a center, and this center is going to give us a reaction force on the rod, and the rod is a beam, and the beam is simply has a simple cross-section for the moment. That's initially we're going to assume that it is a rectangular cross-section with a breadth B and a height H. And this beam need to have The first step to analyze beam deflection stresses is to determine the force distributions. So we will have forces from the shaft on the rod on this side, S on R, and we would have forces from the piston on the rod on this side. So PR is the piston on the rod. We have one force that has a resultant. So this is the resultant, we're going to call it phi, and this is piston on the rod. And cap phi has two components. One is axial, and one is transverse to the rod. And similarly, there will be a resultant force here, phi, that comes from the shaft, and phi has two components, one axial and one horizontal. The motion of the rod is reduced to the motion of a particle, and it has acceleration, and the acceleration now g double dot is vector, and therefore it would have two components. One is tangential and one is axial, and these are going to be dynamical forces, m g double dot tangential and m g double dot axial. These will be the forces coming from inertia. In addition, I have a torque, and the torque is concentrated, and that torque is associated with the rotational motion of the rod, and rotational motion is the polar moment of inertia times the angular acceleration gamma double dot. So that description, the dynamical description, gives us equations of motion, and the equations of motion, we have one equation of motion here for the piston, and we have two equations of motion for the rod itself. So in the green here, I have one equation of motion, linear momentum conservation, and then one equation of motion based on the conservation of angular momentum. So let's look at the piston equation. The piston equation has the mass times its acceleration, P double dot, is equal to the sum of the forces. And the forces, we have one force from the pressure times the area in the J direction, and then one force from the piston on the rod, and then another force from the cylinder on the piston, and that's in the I direction. For practical purposes, this force is very small and will be ignored for the analysis. On the other hand, the motion of the rod itself is reduced to the motion of a particle with mass times acceleration is equal to the sum of the forces, and I have two forces on the ends. One is phi PR and the other one is phi SR, and these are vectors that have, each one of these has two components. And then I have the angular momentum conservation gives me J times gamma double dot in the K direction, which is out of the paper, should be equal to the moments that are applied. The moments have to be in vector form, and the vector moment is the cross product of a force times a distance or arm length. So this is the force times its arm length, G minus P, and another force from the shaft on the rod times its arm length, which is G minus R. All of this is written in vector form, so we have to write equations in component form. The first one is reduces only to one equation because it is in all of the components of the force are constrained to move in the J direction because it's a piston. But the second and the third, each one will have two additional equations that we can split, one in the X and one in the Y direction. And we have a task for this project, and the task is to derive the equations for the reactions on the left and the reactions on the right, that is from the cylinder, from the piston on the rod, and from the crankshaft on the rod. These are four forces in X and Y, and we want to write the forces in terms of the driving system. And the driving system for us is a pressure, so this drives the rod, and accelerations, so in terms of accelerations and pressures. So once we know input to the problem is pressure as a function of angle and acceleration coming from the kinematics, we plug in here and plug in here and find the phi, and then plug in the phi successively and solve this system of equations. And that is what we have a MATLAB code to solve the system of equations and give us these forces as a function of the angle at any point, the crank angle at any point in time. So this is an exercise for us to do as part of the project, and we will now move on to the next task. The next task is going to be on utilizing stress analysis with the finite element method. And we will not spend the time on how the finite element method is theory. We're not going to spend the time on the theory of finite elements, but we will apply it. And the application that we will have is through the utilization of the COMSOL software in the beginning, and if we get successful at it, then we would use also Abacus towards the end of the course. So for COMSOL, we would do 2D modeling with the COMSOL software, and the first step in COMSOL is to build a 2D model. We can build it geometrically, as you can see here, within COMSOL itself, or we can build it using SolidWorks and then import that into COMSOL. So we could do either one of these two steps, or simultaneously you could do this and that at the same time to gain experience. And the idea is that once you have a 2D model, you can extrude it, and then when you extrude it, you have a thickness that can give it mass, and it becomes like a 2D model that can be analyzed with these forces. So if you look now at the forces on the system, I have these 1, 2, 3, 4 forces and a concentrated torque that would be applied into the 2D analysis to give us the distribution of stresses. Before I go there, I might want to make some comments on what do we do with these forces. So if we have the forces determined, then we would do like beam theory. And beam theory is familiar to us. We will cover the aspects that we didn't learn before in the next couple of weeks. And beam theory, the first step is to use forces that are derived before at the ends of the rod to create the shear force diagram, SFD, shear force diagram. So there's going to be a shear force diagram all over the rod. We would know the level of the shear, transverse shear force, and including the reactions and including the concentrated force at the CG. Once I do a shear force diagram, I can also integrate it and determine the bending moment diagram, BMD, bending moment diagram. And the bending moment diagram gives me a distribution of moments along the rod. And if I consider it as a simple beam, then from the bending moment diagram, I can calculate stresses. And the stresses are two parts. One would be axial, and axial is due to forces along the axis of the rod, and the other one is bending, and the bending is due to the moments that are applied on the rod. We will, if the rod is very thin, we will ignore shear stresses in the rod. And once this is done for us, then we could actually have a situation now. So number one, we have the shear force diagram. Number two, we have the bending moment diagram. Number three, we can calculate sigma. Number four, we can calculate deflection, V. And the deflection is everywhere. So all of this can be done at a specific crank angle or a specific time correspondingly, and therefore it's very repetitive. Therefore we use MATLAB, and MATLAB we have snippets of code that are already prepared for you as to mimic, and then you add your input to it, and then you produce plots at this point of various things, moments and shear force and so on. So that would be like the preliminary stage of the calculations where we actually have performed analytical analysis. This analytical analysis is going to go into the 2D modeling, or will precede the 2D modeling to guide us so that we are not too far away from the more accurate calculations. And that is what we have here for COMSOL, where we have stress concentrations at various points in the rod. So we have, you can see there's a contact stress here, and these contact stresses come from the interaction between the connecting rod and pin on the piston side, and the interaction between the connecting rod and the crankshaft on the other side. Such interaction can produce stress concentrations. So the question is this stress too high for failure, or do we have other stresses and at specific corners? And what kind of deflections do we have in the rod? The deflection is too excessive. So that kind of analysis leads us to the next step in our quest for optimization, and that is to use failure theory that we will learn in the course to assess whether the connecting rod meets design criteria, or to determine whether it is actually optimal. So the objective is to optimize the connecting rod for minimum size. So whatever size we have at this point, we'll do fatigue analysis first. And the fatigue analysis, actually before fatigue analysis, we will have to use a static failure criteria, like not exceeding yield point or a fraction of the yield point, to say that under static conditions we wouldn't have failure. But most likely the failure is caused by fatigue or fracture. So the fatigue analysis is based on the SN curve. This is the S and this is N. S is the amplitude of a fluctuating stress, and N is the number of cycles to failure. So every material, if I use steel 4340 for example, then I can go to a website, or I can go to a data book and find the data described by a curve similar to what you see on here. And this curve is the SN curve. And it has a relationship between the stress amplitude for each fluctuation and the number of cycles to failure. However, this type of analysis, since we have we're going to find many fluctuations in the rod, and there's so many points that if we take a volume element along in every different piece of the rod, each volume element is going to see different fluctuations. Then we use another MATLAB program that we wrote, and this MATLAB program is linked to COMSOL to determine the amount of damage accumulated per cycle. In other words, the SN curve is when you have 100% damage, you reach a certain number of cycles of failure. Here, incrementally for each cycle, you get a certain amount of damage. And this is some kind of example here that we have. Highest damage point is shown here. So you get like a damage distribution, some more damage here, damage here. So these are potential failure points that we need to investigate further. So the next step is to assume that the connecting rod is manufactured with a certain process and the surface has a certain finish. Usually we use a non-destructive evaluation to determine the minimum crack size that exists anywhere in the rod. We could use ultrasonic, for example, that gives us a minimum crack size of 1/1000th of an inch. Or if we have very expensive connecting rod, we could even use X-ray tomography to ascertain a much smaller initial crack size. This initial crack size is going to be described by linear elastic fracture mechanics, LEFM, and using an equation that is based on the Paris law, the very well-known Paris law, in which the crack is dA by dN, then the rate of change of the size A with respect to every cycle. We have a function that we will introduce, and this function will be integrated to grow the crack until we get failure. So having done that, it gives us really the ingredients to do an optimization. So the optimization is that I have a geometry and I want to parametrize it. So the parametric description of the geometry is given by geometric values. And these are 4 radii that describe the 2 ends, like circular ends, and a depth or thickness of the rod, and a length of the rod. So we can vary these in different ways. Of course, 6 parameters is a lot, but we can scan this space and reach an optimal design. So the process starts, as we mentioned, from a load analysis, and then we use beam theory to determine roughly stresses and deflections. And once we have done that, then we can establish a 2D model in COMSOL and check to see if that is done with finite element. And then once this is done with finite element, we determine lifetime based on fatigue, lifetime based on fracture. If the lifetime is infinite, then it means that the connecting rod that we designed is too big and too heavy. So we have to go back and reduce the size and reduce the mass, because that's the objective, is to reduce the mass and the cost of the rod. And if it is not feasible, then I go back and change dimensions. If I reach now the minimum size that is possible to give me the lifetime that is needed for the design, then I now can proceed to the final step, which is creating a very detailed 3-dimensional model, introducing it into Abaqus, and finalizing the analysis for the connecting rod. In order for us to ascertain the lifetime, then we usually do not base our decision on local values of the stresses obtained from the finite element. We apply the ASME design code with objective of finding a good value for the safety factor. So in order for us to determine a safety factor, we choose a critical path. So a path is a cross-section. This is path 1. Another path 2 is like here, another cross-section, because it might fail here, another cross-section in the middle. So you can choose your own paths. And each path now, we do not look at every point along the path, but we do some kind of averaging because that eliminates numerical errors that are local. So the averaging gives us an average value for each component of the stress, and the average value is broken into a bending component and a membrane component. We'll get into that into the design, and combined by the von Mises type criterion. And once we get these so-called stress intensities, P is a stress intensity, which is based on, it's like a stress based on von Mises, has membrane, it has bending. Then we apply a criterion, we bring in the data from materials and determine the maximum possible allowable stress, and the allowable stress in the ASME code is 1/3 of the ultimate or 2/3 of the yield, whichever is smaller. And then we can determine a safety factor here based on the ratio of 1 in SM divided by the total stress in von Mises sense times 1.5. So these are kind of things that we will learn as we move on in our analysis. The final step, obviously, some of us will be able to do it, some may have difficulties, so we have to be a little bit flexible. We can model the three-dimensional connecting rod. As you can see, this is with made of with the SolidWorks. And SolidWorks, you have more detail, like for example, fillets here, fillets here, fillets here, and then this is carved. So there's more structure to reduce the mass and redistribute the stress in 3D. And then I introduced that in Abaqus. These are the forces, the boundary conditions. And this is the mesh in Abaqus that I can create in 3D, and then I can do 3D analysis to ascertain the results that I obtained from 2D. So it's progressive. First, analytical beam theory. Second is 2D. Third is 3D. And 3D, you can use Abaqus or COMSOL. So we don't have any problem with using COMSOL. If you're familiar with it, Abaqus will give us a little bit more experience. Now I spent a few minutes on grading. So what will happen is that we want to derive the kinematics, the dynamics, the shear force diagram, bending moment diagram, the applied beam theory, and hopefully do a two-dimensional model by the 4th week. So by the 4th week, we have done all of that, and then we submit a report, and the report is at the end of the 4th week, not the beginning, at the end. And the report is 30% of the grade, total grade of the report, of the final report. So the final is 70%, and the preliminary report is 30%. We will give you a template to fill in as a report, and then you will submit in PDF form, and you will cover abstract, introduction, engine operating conditions, load analysis, preliminary analysis of beam theory, 2D modeling, and then you achieve the final objective, which is submitting this report by the 4th week. By the end of the 10th week, we have finished everything now in the design, and I have a final report, and I now improve on the first part here. So this is here, improve on what you've done before, and then some new material that you will fill in that relate to lifetime analysis, fatigue, fracture optimization, and 3D modeling to finalize your report and submit it. So this is kind of an overview of the Connecting Rod project. I think it's going to be a lot of fun. And with this, we have reached the end of this lecture. Thank you for watching, and we'll see you in the next video.